We shall move on to the next chapter, the p block elements. P block elements are those group of elements in which the last electron enters the outermost p orbital. We know that the number of p orbitals is equal to 3 and the maximum number of electrons that can be accommodated in a set of p orbitals is equal to 6. Therefore, we have 6 groups of p block elements. Group 13, 14, 15, 16, 17 and 18 are the p block elements. In p block elements, the general outer electronic configuration will be Ns2Np 1 to 6. The maximum oxidation state shown by a p block element is equal to the total number of valence electrons. It is also found that the number of oxidation states increases towards the right. In p block elements, it is found that the oxidation states of an element differ by a unit of 2. For example, consider tin. It exhibits 2 different oxidation states, Sn2 plus and Sn4 plus. So the oxidation states differ by a unit of 2. Another important point regarding the p block elements, lower oxidation state becomes more stable down the group. It is due to inert pair effect. Non-metals and metalloids exist only in the p block. Non-metallic character decreases down the group. We know that metallic character increases down the group and hence non-metallic character decreases down the group. Heaviest element in each p block group is most metallic. Non-metals have higher ionization enthalpies and higher electronegativities than metals. We know that metals form cations whereas non-metals form anions. A highly reactive non-metal reacts with a highly reactive metal to form ionic compound, whereas compounds formed between non-metals are covalent in nature. Non-metal oxides are acidic in nature. For example, we know that carbon dioxide is acidic in nature. Metal oxides are basic in nature. For example, magnesium oxide is basic in nature. First members of p block differs from the remaining members of the group. Boron, it exhibits a maximum covalency of 4. It is because boron has no d orbitals. But aluminium can exhibit a maximum covalency of 6. It is due to the availability of d orbitals. These elements can form pi bonds. For example, consider carbon-carbon double bond. We know that the double bond is made up of 1 sigma bond and pi bond. So these elements can form pi bonds. But heavier elements do not form pi bonds. Now consider nitrogen and phosphorus in +5 oxidation state. Nitrogen exhibits +5 oxidation state in nitrate ion NO3- and hence we can say that nitrogen forms oxoanion NO3-. Similarly, consider phosphorus. It exhibits +5 oxidation state in phosphate ion PO4-3-. Hence phosphorus forms oxoanion PO4-3-. So let us now learn about group 13 elements known as the boron family. The group 13 elements are boron, aluminium, gallium, indium, thallium, nihonium. Boron is a non-metal, whereas aluminium, gallium, indium, thallium and nihonium are metals. Occurrence of group 13 elements. Boron exists as boric acid and borax. The isotopes of boron are B10 and B11. Aluminium is the most abundant metal and it is the third most abundant element in the Earth's crust. The ores of aluminium are bauxite and cryolite. Gallium, indium and thallium are less abundant. Nihonium is a radioactive element. Electronic configuration of group 13 elements. They have Ns2np1 outer electronic configuration. For example, consider boron atomic number 5. The electronic configuration can be written as 1s2, 2s2, 2p1. Aluminium atomic number 13. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So they have Ns2np1 outer electronic configuration. Aluminium has noble gas core, atomic and ionic radii. We know that atomic radius increases down the group, but deviation is seen in group 13 elements. Atomic radius of gallium is less than that of aluminium. It is due to variation in the inner core of the electronic configuration. It is due to the presence of 10 d electrons. The d electrons offer poor shielding effect for the outer electrons. So this is the reason why atomic radius of gallium is less than that of aluminium. Ionization enthalpy. Ionization enthalpy values do not decrease smoothly down the group. There is a decrease in ionization enthalpy as we move from boron to aluminium. It is due to an increase in atomic size. The discontinuity in the ionization enthalpy values between gallium and aluminium and indium and thallium are due to the inability of d and f electrons, which have low screening effect, to compensate the increase in nuclear charge. First ionization enthalpy is less than second ionization enthalpy, which in turn is less than third ionization enthalpy. Electronegativity. As we move down the group, electronegativity first decreases from boron to aluminium, then increases marginally. This is because of the discrepancies in the atomic size of the elements. Physical properties. Boron is a non-metal. It is a hard solid. Boron has high melting point. It is due to strong crystal lattice. Rest of the members are soft metals with low melting point and high electrical conductivity. Gallium has low melting point. It has high boiling point. Since gallium has high boiling point, it is used for measuring high temperatures. Density increases down the group. So these are the physical properties of group 13 elements.